Hey guys, it's me, Mrs. Reba, trying something a little different per your request. Try to make this a little more personal for you guys. So this is one of the reasons why today's notes might be different for you, because you might be viewing these as a video. You also will notice here that it says that I'm also not going to be identifying what you should write down. You should pick it. Other than working through the examples, you should always be working through the examples. Today's lesson is all about graphing linear patterns. You can take a minute here to take a look at the learning target. Also, at some point in time in this video, you may want to pause, rewind, or fast forward the video. So while you take a moment to make sure that you know how your computer does that, I'm going to tell you a really funny math joke before we start the actual math content. So go ahead, practice, pause, fast forward, rewind. The funniest math joke that I've heard today, what did 0 say to 8? Nice belt. Get it? If you don't get it, we can talk about it on Friday. Actually, if there's anything that you don't understand in these notes, feel free to email me, or we can always talk about it in the next class. In this case, would be on Friday. So let's go ahead and dive into graphing some linear patterns. As always, the textbook provides some great examples, and question marks should be added wherever you have a question. Let's start. Constant increase patterns. These happen, of course. It's any situation in which value increases by a constant amount. Some examples would include the following. Please press pause. Take a moment to read these. We'll continue when you're done. After reading each of these situations, you may have determined what makes each of these a constant increase. In part A, the fact that the pool water level of the pool is rising or increasing 3 inches every hour. This is a constant increase because it's going to happen every hour. In our landfill example, this is a constant increase because 1,600 tons is being added, increasing, to the landfill every day, constantly. In our yoga studio, our $35 registration fee, and then charges $20 for every class. Here's our constant increase, $20 every class. And in our humidifier, we can see that the humidifier is adding 0.12 of a gallon of water per hour to the air. Here's our constant increase. It's happening every hour. We're going to see something similar in a constant decrease pattern. This might not come as a surprise that something is going to be constantly decreasing or going down. Any situation in which value decreases by a constant amount. Here are a couple of examples. Please press pause to go ahead and read these examples. You should make it your goal to identify the constant decrease. We can see in example F that this is a constant decrease situation because the water level in the tank will decrease as the water is dispersed into the air at 1/10 of a gallon per hour. Jeremy's friends are descending at 1 meter per minute. This is descending or decreasing 1 meter every minute. Sharon's pool is full of dirty water, so she needs to empty it. We can see that this is a constant decrease because the water level is going down 6 inches per hour. That means every hour. John's situation is a constant decrease because his total number of hours are decreasing by 4 after each week that passes. Once we're able to identify whether something is a constant increase or a constant decrease, we should start to think about graphing. In order to graph the situation, we have to identify an x variable. The x variable is a dependent, meaning that it does not depend on anything else in the situation. It will always continue in the same way. For example, time. Time always passes, therefore it is an independent variable. Identify the dependent variable as y. This is the quantity that changes at the constant rate. Although it is changing constantly, it depends on something else. We would then use a table to identify pairs of numbers that fit the situation. X equals 0 value is always the starting amount. And then we would graph our ordered pairs to see the line. An example. Please familiarize yourself with Sharon's pool one more time. You will most likely remember this situation as a constant increase because Sharon's pool is starting out with 1 foot of water, and the water level is rising 3 inches every hour. If we take a look, it is important for us to identify the independent variable and the dependent variable. In this situation, h, the number of hours, is our independent, because the height of the water, w, will depend on how many hours have passed. Let's go ahead and take a look. We're going to use a table to help us out with this. Again, we're going to use x as the number of hours passed, y as the current water level in feet. As we take a look here, after 0 hours have passed, of course there's going to be 1 foot of water. That's where it's starting. After 1 hour has passed, we are going to see actually 1 1/4 feet of water. Conveniently, 3 inches happens to be a 1/4 of a foot, 3 out of 12. We can see again a possible calculation over here, 1 plus the 1/4 of a foot. After 2 hours, we will see 1 1/2 feet of water in the pool because another hour has passed and another 1/4 inch has been added on. After 3 hours, we'll see 1 3/4 or 1.75 feet of water. Again, we can see in our possible calculation on the right side over here, 1 plus the 1/4 plus the 1/4 plus the 1/4. This pattern would continue. In the 4th hour, there would be 2 feet of water. We always like to extend in algebra the pattern. What would happen if we didn't have the number, but kind of directions to calculate the water level after h hours. And in this instance, we can see that the water level would be the original 1 plus the 1/4 of a foot for every hour. So we would multiply by the number of hours, and this would be equal to, or this would give us our W. This is what we're talking about when we say a linear equation. As we take a look here, continuing on, here's our table that we saw. We're going to need to actually go ahead and make the graph. In order to make this happen, we're going to go ahead and grab a piece of graph paper. We are going to draw in our x and y axis. Here again, our independent variable goes on the horizontal, hours of filling, and our dependent variable on the vertical axis. We need to pick a good scale to use. It doesn't look like, actually we know from the situation, being that the pool is only 5 feet deep, we don't need a whole lot of y values here. I think it's pretty reasonable for us to pick a scale of 1 for the horizontal axis. Kind of looks like 2, but it's technically a 1, 0, 1, 2, 3, 4. It counts each step, and a scale of 1/2 on our y-axis. 0, 1/2, 1, 1 1/2, 2, 2 1/2, 3, and so on. We'll graph each of our ordered pairs. 0, after 0 hours, we are at 1 foot. After 1 hour, we are at 1.25 feet. After 2 hours, we're here at 1 1/2 feet. After 3 hours, we're here at 1.75 feet. And after 4 hours, we would find another value here right at 2 feet. If we take a look, these values are starting to line up. Not a coincidence. We actually can go ahead and create the line. As we are graphing that line, we are graphing the equation W equals 1 plus 0.25h. Taking a look here, these graphs can be kind of handy. We know that the pool was 5 feet deep. If we take a look at where the red line goes through the 5 foot mark, that's going to happen over here at 16 hours. So we know that it will actually take 16 hours for Sharon to fill her pool. This is a great example of a constant increase. Feel free to rewind and try any of the other constant increases to see how you can do. Let's take a look at a constant decrease. Let's deal with John and his volunteer hours. Again, we need to identify a dependent and an independent variable. In this case, we can see our constant decrease again as 4 hours per week being taken off his volunteer hours. How many hours H does he have to complete after W weeks? H here is our dependent variable because it depends on the number of weeks being our independent variable. We can go ahead and set up our table. Again, the 0 weeks, after 0 weeks have passed, we know that he has 52 hours to complete. After 1 week, we know he's down to 48, 52 minus 4. After 2 weeks, we know he is down to 44. 52 minus 4 minus 4. And after 3 weeks, he's down to 40. And after 4 weeks, he's down to 36. Again, we can kind of see our pattern here because in algebra, that's what we do. We look for patterns. If we want to put this information on the graph, again, we'll have to draw on our x and y axis. In this case, we are going to have to choose a scale larger than 1. If I count by ones, I'm not going to get to the 52 hours necessary for 0 weeks. So it kind of makes sense to, again, count by 1 in the weeks department down here on the horizontal scale. I decided to use a scale of 4 on the vertical axis. 4, 8, 12, 16, 20, 24. I'm going to go ahead and graph each of the points that I can see here, with the final point from my table being here at 4 weeks and 36 hours. Again, we can see that things are lining up nicely. We can see the line. This graph is really useful. I can tell that John will be down to 0 hours here at 13 weeks. Again, this has been an example of a constant decrease. Feel free to rewind and try any of the other examples from the constant decrease. We will meet on Friday to go over your questions. Have a fun day.